Hello everyone and welcome back to MV Tutors. It's been a minute, but we're back. We're back and we're looking at the 2022 paper, okay, the November paper written last year. So we're going to go straight to question 1 and see how we can do this thing, especially now for those who are writing the supplementary in March. This is a good place to just recap. Okay, so let's have a look at this question 1. Multiple choice question. So it says in question 1.1, which one of the following combinations consists of only scalar quantities? Remember, scalar quantities have magnitude but no direction. Okay, they're not like vectors. So option A, velocity, that's a vector. Speed and time, yes, scalar quantities. B, time, distance and speed, yes, that's an option. All right. C, acceleration, speed and distance, acceleration is a vector. D, displacement, velocity and acceleration, all of them are vectors. All right, so B is the correct answer. Whenever you see a correct answer, please don't stop to look at the other options, just to be sure. Okay, and then 1.2, the acceleration due to gravity on Earth is g. And remember what g is? G is basically the gravitational constant, the mass, and the distance between the centers, or the radius. Let's just stick to radius. Yes, because we don't have two objects. If it were two objects, then it would be the distance between the centers. But this is just the radius. And let's just make sure, is it just radius or radius squared? Let's look at the formula sheet. Okay, that is why it's there for us to check and make sure, and it is radius squared. Okay, also don't fool yourself into thinking you remember everything. If you do need to go back and check the formulas, please do so. So that is the one on Earth. That is just g, which is 9.8 meters per second squared. Now let's have a look at what the question says. It says, which one of the following represents the acceleration due to gravity on a planet that has twice the mass and half the radius? Okay, so now we have twice the mass. All right, so it will be g times 2m and half the radius. Okay, so what then do we get? We get 2gm all over a quarter r squared. Okay, now do you see this whole term is our g over there? Okay, and then 2 divided by a quarter is 8. Okay, there are 8 quarters in 2, so we have 8g, and that answer would be D. Okay, I did not mean to rhyme there, it just happened. All right, so 1.3, it says a ball is projected vertically upwards from the ground. Okay, projected vertically upwards from the ground and reaches its maximum height after a while. Ignore the effects of air friction. How will the acceleration and total mechanical energy of the ball at its maximum height compare to that immediately after it was projected? Now remember that acceleration, it always remains constant, especially with vertical projectile motion, because an object is in free fall and the only thing acting on it would be the gravitational force. All right, so acceleration remains constant, which is g, which is 9.8 meters per second squared. What about the total mechanical energy? Remember, total mechanical energy is kinetic energy plus potential energy. And even though the kinetic energy changes, for example, it increases as potential energy decreases, ultimately the total mechanical energy remains the same. It is just constant, no matter the position. All right. Had they said kinetic energy, yes, that changes over time. If they said potential energy, most definitely changes with time. But the total mechanical energy, it remains the same. So what answers do we have here? A, acceleration is equal to, and mechanical energy is equal to the one at maximum height compared to the one immediately after it was projected. So if I look at all the options here, option A is more appealing, and it is correct. Okay, so no matter in which position you're in, The acceleration will always be the same, as well as the total mechanical energy. Now let's look at 1.4. Okay, sorry about that. Let me just switch it off. Okay, 1.4. A car travels at constant velocity along a horizontal road. Constant velocity tells us there's no acceleration, right? Now, a constant frictional force acts on the car during its motion. Which one of the following statements about the power dissipated by the engine of the car during the motion is correct? Now, in this case, I would ask, what is power equal to? Remember, power is the rate at which work is done. Okay, and work is equal to force times displacement, cos theta, okay, over time. And what else? We know that delta x over delta t, that can be velocity, right? So we have FV cos theta. So we have quite a few options here in terms of power. So we can see what we focus on depending on the information that we have. Let's go back. So it travels at constant velocity, okay? And there's a constant frictional force that acts on it. So we know our force is friction, which is in the opposite direction, so it'll be negative. And then there's a constant velocity, and yeah. So now the power dissipated by the engine of the car during the motion, what happens to it? Is it zero? Does it increase? Does it decrease? I believe it remains constant, okay, because you have a constant frictional force acting on it. Your velocity is also constant, okay. The magnitude would be negative, but overall it is constant, so I would go with D. 1.5. Block X is placed on a horizontal table and is connected to block Y by a light inextensible string passing over a frictionless pulley as shown below. A constant frictional force acts on block X while it moves to the right. Okay, you know, friction is in the opposite direction. P, Q, and R are points on the table such that the distance from P to Q is equal to that from Q to R. When block X reaches point Q, the string is cut and block X continues to move towards point R. Okay, remember, it will move in the same direction unless an external force acts on it. Okay, so because of inertia, it will continue moving, but at what rate? Ignore the effect of air friction. Consider the following statements. Before we even go there, so you had this block Y that was assisting block X to move to the right. Yes, you had some friction which was slowing it down. And once block Y is cut, there isn't that anchor that keeps, there's no force. So block Y acts like a force for block X, right? So if there was no friction, block X would have continued moving, but there's an external force called friction that is acting on it. So eventually it will stop after Q on its way to R. All right, so let's look at the statements. Number one, the work done by the frictional force acting on block X is greater when the block moves from point P to point Q than when the block moves from point Q to R. No, remember, work is force times distance. The distance from P to Q is equal to that of Q to R, and the friction force is the same, so no. Two, both the momentum and kinetic energy of block X decrease when the block moves from point Q to R. That is true. Remember, both momentum and kinetic energy depend on velocity, and the velocity will definitely decrease from point Q to R, so that is true. Three, the total mechanical energy at block X remains constant when the block moves from point Q to point R. No, it doesn't. Okay, so now let's see. Which of these statements above is or are correct as block X moves from point Q to point R? So far we know it's 2, right? Option 2. And I can see that it is B. Okay, so we will go with B. 1.5 is B. 1.6. Light emitted from a distant star contains a spectral line X of frequency f. The spectral lines of the star when observed on Earth are red-shifted. Which one of the following combinations of the observed frequency of spectral line X and the motion of the star is correct? So, what are we expecting with the observed frequency? By the way, if you want to listen to or see a lesson, just reminding yourself of the red and the blue shift, there is a video on it. Look at our playlist under physics and you'll see this. There's a specific video called the red and blue shift. Okay, have a look at that. I'm not going to go through the theory now. But the observed frequency will be smaller than f. Okay, and because it will be smaller than f, we're only looking at options C and D. Now let's see the motion of the star. Is it away from the Earth or towards the Earth? Alright, so it will be away from the Earth. Hence, 1.6 option is C. 1.7. A proton and an electron are distance r apart. The magnitude of the electrostatic force that they exert on each other is F. Which one of the following graphs shows the relationship between F and r squared as the proton and the electron approach each other? Remember that equation where we have F is equal to the gravitational constant. You have mass of the one, mass of the other divided by r squared. Okay, so F and r squared are inversely proportional. And because they're inversely proportional, it is tempting to go with D, but the r squared is more, it renders a curve. Okay, think about a quadratic equation, but not the full one, not the full parabola. So instead of D, which is just a straight line, we'll go for option C. Okay, yeah, 1.7 is C. And now 1.8. Not a lot of people are fans of electric circuits, but they're quite fun when you understand them. I also struggled. I won't lie, but eventually I had to get it. So yeah, let's look at 1.8. The EMF of a battery is E. Okay, that's actually called epsilon. And its internal resistance is R. The battery is connected to 3 resistors, okay, and 4 voltmeters, as shown below. The resistance of the conducting wires is negligible, while the voltmeters have very high resistances. Which one of the following equations represents the reading on voltmeter V1? So that is V1, that is reading the potential of the battery and the internal resistance together. Okay. So yeah, what is the reading on voltmeter V1 in terms of the readings of other voltmeters? Okay, what do we know about that voltmeter one? All right, so A is V1 equal to V2 plus V3. Remember V3 and V4, because they are in parallel, they're basically equal. Okay, so is A an option or B? It will be half of V3 new. C, it will be V1 is equal to V2 plus V3 plus V4. No. If every resistor was in series, then yes, you would add the voltages. So C is for only with resistors in series. Now D, is it V1 is equal to V2 plus 2 times V3? No. Remember, V3 and V4 are actually equal to one another. Alright, so the total voltage read, I almost said readed, the total voltage that is read at V1 would be a combination of V2 as well as V3. So the answer would be A. Okay, so 1.8 is A. Alright, and then 1.9. Okay. An AC generator consists of a coil which is rotated in a magnetic field. The EMF time graph for one complete rotation of the cell is shown, or the coil is shown below. Alright, so we can see that the EMF there is 150 over, over 0.2 seconds, the full wave. Now, if the speed of rotation of the coil is now doubled, which one of the following graphs is correct? Okay, so in doubling it, are we multiplying the EMF by 2? Okay, does it mean that the frequency will be much less? So instead of taking 0.2 seconds, you're going to get 0.1. So yeah, what option do you think we should go for? Okay, so if you look at A, it remains the same basically. So that's really not an option. If you look at B, the amplitude has been doubled. Okay, that is really not an option either. It is partly right. Okay, and then if you look at C, the amplitude has increased and the time in which it takes to complete a full wave, or the period rather, has been decreased. This looks quite correct. But let's look at D. So only the period has decreased. Okay guys, in this case, C is the correct answer. Your amplitude will double, but your period will halve. Okay, so 1.9 is C. And we are almost there. We are there actually. The last question. White light is passed through a cold gas and then through a prism as shown below. Okay, again, I do have a video on this, so go and have a look at the playlist of the physics videos. So now a line spectrum is observed on the screen. What kind of line spectrum do we have there? Which one of the following correctly describes the energy transition of the atoms of the gas and the type of line spectrum observed on the screen? So energy transition, A, is it from a higher energy level to a lower energy level, or is it from a lower to a higher energy level? Okay, in terms of energy transition, it will actually be from a lower to a higher energy level. So now we have option B and D available to us. So we're not going to bother with A and C. Yes, we're not going to bother with A and C actually. Hint, hint, as we go to the voting stations next year. And now the type of line spectrum. Okay, since we're looking at B and D, is it emission or is it absorption? Absorption. Okay. So the answer here in this case, because we have cold gas and not hot gas, it will actually be absorption. So the answer then for 1.10 would be D. Please guys, make wise decisions when you go and vote. Next year you'll be old enough, so do the right thing. Hello everyone and welcome back to MV Tutors. I'm Solo and I'll be looking at question 2 with you guys. Remember, we're still doing the November 2022 exam, paper 1, physical science. Alright, so let us get right into it. This is question 2. And it says, crate P of mass 1.25 kilograms is connected to another crate Q of mass 2 kilograms by a light inextensible string. So we're not going to consider the weight of the string in any of the calculations. Thank God for that. The two crates are placed on a rough horizontal surface. So we know there's some friction, okay? A constant force F of magnitude 7.5 Newton acting at an angle theta to the horizontal is applied on crate Q, as shown in the diagram below. Both the crates accelerate at 0.1 meters per second squared to the right. So you have this applied force pulling on Q, and Q is like, I'm not going alone, I'm bringing P. Okay, and there's this string that's going to help us get there, wherever there is. So crate P experiences a constant frictional force of 1.8 Newton, and crate Q experiences a constant frictional force of 2.2 Newton. The reason why we have different frictions could be that P and Q are made from different materials. So the surface could have the same roughness, but P and Q has been made of different materials, or this surface that P and Q are on is different, okay? On one portion, maybe it has been too rough or too smooth, but yeah, there are factors that could warrant the friction forces being different, okay? But let's just get straight to the question and let's not waste any more time. So 2.1 says, state Newton's second law of motion in words. All right, I normally say if you forget the theory, please try to get an equation that will at least help you remember. And the equation that is applicable to Newton's second law is the resultant force being equal to the mass times acceleration. So we would start by stating Newton's second law in the following ways. When a resultant force acts on an object, it causes the object to move in the direction that the force has been applied. Okay, it doesn't make sense that you pull something yet it is pushed away. Okay, so that object will move in the direction where the resultant force has been applied, firstly. And instead of saying move, you could say the object will accelerate in the direction of that resultant force. Now let's talk about the acceleration for a moment. The acceleration will be directly proportional to the resultant force, but it will be inversely proportional to the mass. So if you apply a very big force, the acceleration will be quite high, but if you have a heavy object, the acceleration will decrease. Okay, so that's basically Newton's second law of motion in words. You can explain it. I'm not going to write it down. So 2.2 says draw a labeled free body diagram for crate P. Okay, so now we can see here that firstly we have the weight of P, or you could say force of gravity, either will be fine. And then there's also the normal force, all right? And then remember this friction that is opposing the motion. Okay, so you have your friction force, and then you have the tension force coming from the string, and it's going to be slightly bigger because it's moving to the right along with Q. Okay, so we will have tension. Okay, and that is it. That's our free body diagram. Now let's get to 2.3. So it says calculate the magnitude of the tension in the string. Aren't we thankful we wrote or we drew down the free body diagram? You can see what's going on. If we're choosing right as positive, it means tension will be positive, and we're going to subtract the friction force. And we know that, actually let's start off like this. We should just write down the equation. Resultant force is equal to mass times acceleration. And what is the resultant force? We have tension moving in the positive direction, and we have friction force that is opposing that motion. They told us the mass of P is 1,25 kilograms, and the acceleration they also told us it is 0,1. Okay, 0,1 meters per second squared. We're looking for the tension, right? So I'm going to just take everything to the other side. 1,25 multiplied by 0,1 plus the friction force, which they gave to us. At least you don't have to work out much. It's been given, and it is 1,8 Newton. All right, and then once we calculate that, we have 1,25 multiplied by 0,1 plus 1,8, and we get 1,93 Newton. Do not forget the unit. Okay, so this is the first portion of 2,3. Now 2,3,1. The magnitude of the angle theta. I'm thinking we draw the free body diagram of Q because that's where theta is. Okay, I mean it's only 3 marks. You're not gonna get the marks for drawing the. Well, I think you're not gonna get it, but this is really for you, especially for those who are visual learners like myself who just want to see what's going on. So we have the mass. Let me just write down everything. We have the mass and we have gravitational acceleration. Then you get your normal force. All right. And then you have the friction force, which is, I'm just going to put small f for friction, which is 2,2 Newton. And then there's also the tension force, which is 1. Oh, no, it's actually less. So let's not draw a bigger arrow. So tension is 1,93. And then we have the applied force, right? So this force applied is 7,5 Newton. And we're going to actually resolve it in its x and y components because it makes life easy for us. All right, because we have theta over there. So this will simply be 7,5 cos theta, and that'll be 7,5 sine theta. So I believe we have enough information to calculate what theta could be. Let's get back to our blue pen. And yeah, let us resolve all the forces in the y. No, in the x. In the x, let's deal with the x. We know more about that. Okay, so your resultant force again is equal to mass times the acceleration. And we have our 7,5 cos theta minus 1,93 from the tension force minus 2,2 from the friction force, and then the mass is 2 kilograms multiplied by the acceleration, which is 0,1. Okay, so really our unknown here would be theta. Okay, let me see if I can write it in terms of theta. So theta will be equal to arc cos, and there's a whole lot going on. So we have 2 times 0,1 plus 1,93 plus 2,2, and that is all divided by 7,5. Okay, so we can put all of this into the calculator. Sometimes it's dangerous to do something like this. It's better to take it step by step. So you will determine where you are and do what's actually good for you, what you understand. I just like writing things in terms of what I need, depending on how easy it is or how easy it looks. Because sometimes some things may look easy, and then all of a sudden you try it out and then you're seeing flames. So the angle would be 54,74 degrees. That is what theta is equal to. And I believe we are done with question 2. Nice and short.
Well, good day to you. If you're watching this, please take a moment to like and subscribe to our channel if you haven't done so. Otherwise, we're still doing question number 3. Well, we're about to do this question. This is the physical science paper 1 of 2022 November. Okay, let's get right into it. Question says a ball is thrown vertically upwards from the top of a building of a height 25 meters with a velocity of 12 meters per second. That's the initial velocity. On its way down, the ball passes a door which has a height of 1.5 meters and then strikes the ground as shown in the diagram below. Ignore the effects of air friction. And the first question, which is what they always like to ask, is define, which is a definition. Define free fall. Well, that is just basically, let me just say, it's motion under the influence of gravity. Motion under the influence of gravity. Just like that, gravity. Oh, that's it. Okay, let's look at question 3.2.1 now. It says calculate the time taken for the ball to reach its maximum height. Now, whenever you get these questions, you kind of always have to have a little diagram for yourself. So the maximum height, this is the top of the building. Ball goes like that. That's the maximum height over there. I'll call this point A, and I'll call the maximum height point B. Now, you have to choose the right formula for this, okay, given the variables that you have from the question. So, if, for example, I want to use this formula where it's V, let me just check it here. V final is equals to V initial plus acceleration times time, change in time. Okay, now this is one formula that you can pick because what we are really calculating here is the time. So make sure whatever formula you pick has a time variable over there. So we're gonna look. First of all, let's choose a direction. We're gonna choose upwards as positive, right? So now our final velocity when the ball reaches point B, our final velocity is 0 there because it goes up and it reaches the maximum point, which is 0. Our V initial we've been given is 12. Now let me ask you, is it positive or negative? If you said positive, you are right because we chose upwards as positive. Okay, plus acceleration, that's gravity. Now, is my gravity positive or negative? Remember, gravity is always going down. So if you said negative, you are correct. It's negative 9.8. Let's use 9.8 for now. And then T is what we're looking for. So now it's just mathematical gymnastics that we have to do at this point. So what I'll do is take 12 to the other side. So then I'll have minus 12 is equals to 9.8. Remember, this is minus as well. T. And then to solve for T, then that's going to be minus 12 divided by minus 9.8. Now let's get a calculator at this point. All right, there's my calculator. Now I'll put a fraction there. I'll put negative 12 divided by negative 9.8. Oops, did I say 19? I meant 9.8. And it should be negative. Okay, final answer should be positive. Let's change it to a decimal, 1.22. Therefore, T is 1.22. Now let me ask you the units of T. It's always in seconds. So it takes 1.22 seconds to reach up there. That's our final answer right there. Okay, we're gonna do 3.2.2 now. Okay, and it says calculate the velocity with which the ball strikes the ground. Now it's all about choosing the right formula. Okay, and the formula I'm gonna pick for this one is this one right over here. V final squared is equals to V initial squared plus 2 change in y. Okay, now we are looking for the velocity. Okay, we're looking for final velocity. All right, so I'll choose this one. Our initial velocity, now there are many points we could start at. Okay, we already said that was point A there. That's point B. I want to name this point C here, and then the ground, I'll just name it D. Okay, now I want to start this motion from point C. Okay, theoretically, we know that the same velocity that the ball leaves A is the same velocity that is at C, theoretically speaking. The only difference is direction. Okay, so at C is our initial velocity because we want to know velocity with which the ball strikes the ground, which is one velocity. So I'm going to take C as my datum, or rather as my starting point. Okay, so I'm going to say my initial velocity then, since we chose up going down, up is positive, going down is negative. So we have negative 12 squared over there plus 2 times now the change in y. Okay, now let's look at this very carefully. Isn't there a g somewhere there? There is. I missed it. There's an acceleration there, and acceleration is still going down, so it's negative 9.8. Okay, now our change in y, if we look at the height of the building, because C is at the height of the building, it's 25. Now remember, it's we chose up as positive, because our height is now from the top, our change in height is from the top to the bottom, so it's negative 25. Cool. All we have to do now is just put this in a calculator. Let's see what it gives to us. So I'm going to put it exactly as it is. Negative 12 squared plus 2, open the bracket, got negative 9.8, close the bracket, open it again, and put a negative 25, close the bracket, and our answer is 6, 3, 4. Okay, so remember this is square. Okay, so at this point we're just gonna take the square root of 634. Square root of 634, and that's gonna be equals to 25. So then that means that our final velocity is therefore 25.18. Now, what are our units? It's velocity, so that's in meters per second, just like that. Just a quick question. Would it have made a difference if I said my starting point is at A instead of C? Would the answer be different? Well, if you said yes, then you are wrong. But if you said no, the answer won't be different. You are right, because you are squaring it. The same initial velocity there, you're still going to square it, and you'll get a positive value. Any number you square is going to be always positive. Okay, well, no difference. The answer is still going to be the same. Okay, let's do 3.2.3 now. It says the time it took the ball to move from the top of the door to the ground. Okay, that's cool. So we know that the door is 1.9 meters. So what I'm gonna do is that's the door there. Upwards is still positive. Okay. So I'm gonna take the distance from the bottom to the top, and the formula that I'm gonna use is this one. Okay, change in y. Remember, it's all about picking the right formula. Once you've picked the right formula, you let the formula guide you from then onwards. Okay, change in y is equals to v initial, change in t, plus half, okay, a change in t squared. It's a quadratic formula. Okay, so from there we know that from the bottom to the top, the door is 1.9 meters. Okay, our initial velocity, which is calculated it that at the bottom, it hits it at 25.18 meters per second. And then our change in t, that's what we're looking for. So I'll just put it as t plus a half. And then our acceleration is still going down, never changes direction. So it's negative. Okay, t squared. From here onwards, it's just mathematical gymnastics. This is possibly a quadratic formula. So what I'm gonna do is that I'm just gonna put the numbers there. Okay, let's start with this one. What's a half? 9.8 divided by 2. That gives me 4.9 t squared, and it's negative. Okay, plus 25.18 t minus 1.9. So what I'm gonna do now is just put this in a quadratic formula. Remember quadratic formula, that t will be equals to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Okay, so let's put numbers into that. Okay, so minus, I always put the variables in brackets. What's our b? It's 25.18 plus or minus square roots b, once again, it's 25.18, close that bracket, square it, minus 4, value of a is minus 4.9, and then the value of c is minus 1.9. Okay, all of this is under square root. Divide this whole thing by 2a, and a is, what's the value for a? Minus 4.9. There we go. Okay, let's put that in a calculator. Okay, let's put that in a calculator. So we have a minus, open the bracket, 25.18, close it. Let's start with a plus. Square root, open the bracket, 25.18, close it, square that, and then it's minus 4, open brackets, minus 4.9, close the bracket, open another one, minus 1.9, close it, and let's go downstairs. It's 2, open a bracket, minus 4.9. So you put it exactly in your calculator as it is. So our first t value is that t is equals to 0.07 seconds, or 8. 0. Okay, let me make it 2, actually. 2 values there. Okay, like that. 277 seconds. Cool. Now let's go and see what difference it makes if we put a negative there. We subtract, delete that positive, put it negative. What do we get? We get that, or t is equals to 5.06 seconds. Now we have to discuss which one of these answers actually makes sense. Okay, now look at this. 5 seconds is a bit too much for a distance of 1.9 meters, considering that, remember, we solved for t here, right over here, 3.2.1. It takes the ball to reach the maximum height. It took it one second to reach the height, right? And I would imagine that, you know, if we were to calculate the time from that maximum height to the bottom, really it won't be such an exorbitant time, you know. So I can conclude with positivity that this is my final answer here, 0.077. Okay, for a height of 1.9 meters. Okay, right, well, that's it. Okay, let's look at 3.3 now. It says draw a velocity versus time graph for the motion of the ball from the moment that the ball is thrown upwards until it strikes the ground. Use the ground as zero reference. Clearly indicate the following on your graph: the velocity with which the ball was thrown upwards, time taken by the ball to reach its maximum height, the velocity with which the ball strikes the ground. Okay, so that's cool. So what I'm gonna do now is that we're gonna look, remember, we're taking upwards as positive. Okay, that's the first thing. So if we draw, okay, a straight line there, and this side we are really just putting the velocity. Okay, velocity. Now we know that the velocity of the ball, it started with 12 meters and it was positive because it was going up, and we chose up. That initial velocity was 12. Okay, so we'll put 12 right there. Okay, so this is velocity in meters per second. And we calculated that when it reaches, this is point A, okay, on our drawings over here, point A. Okay, when it reaches point B, the ball has 0 velocity. Okay, right there. So that would be, that's 0 velocity. Okay, and this is our time right there in seconds. Okay, so we know that B is 0. Okay, and then we know that at the end, not there, at this side, we calculated that at D, the final velocity is 25.18. And it's going down, so it's actually negative. So let's put it right there. That's negative 25.18. Okay, and then our graph from there we know is a straight line, so I'm going to make it a straight line. It should be a straight line like that. Okay, right, now point B is right here. It's actually right over there. And how much time did it take? We calculated it up there, calculated that time. That was our final time, 1.22 seconds. Okay, so our value over there is actually 1.22 seconds. Okay, is there anything else that we need to add? I'm just gonna make it, I'm just gonna put dotted lines to show that 25.11 is all right over there. So they said clearly indicates the following velocity which the ball leaves it. There it is, it's 12. Time taken by the ball to reach its maximum height. There it is, it's 1.22. The velocity with which the ball strikes the ground, there it is, 25.18. So we are done with this question. Thank you so much. Please, if you enjoyed this and you understood some stuff, like and subscribe our channel. We would really appreciate it. Thank you.
Welcome back to MV Tutors, and we're still at it with the physics paper. So let's do question 4. Don't forget to like our videos and subscribe to our channel. Thank you for spreading the word about our YouTube channel. We appreciate it highly. And yeah, we hope we're making a difference in your maths and physics lives. Okay, so trolley X of mass 1,2 kilograms travels 8 meters per second east and collides with trolley Y of mass 0,5 kg, which is initially at rest. Ignore all frictional effects. The velocity time graph below shows the velocity of trolley X before, during, and after the collision with trolley Y. And we can see that, right? Because for the first 20 seconds, okay, rather from time 20 to time 20,1, it has the velocity of 8 meters per second. And then between 20,1 and 20,2 seconds, just a split second, right? 0,1 seconds, you have the collision. And then at the end, we see that trolley X has a final velocity of 4. Okay, I hope you can see that. On the other hand, with trolley Y, we can see that we have an initial velocity of 0 because they tell us that initially it was at rest. But because of the collision, something must have happened. Okay, so yeah. Now, first question says, state the principle of conservation of linear momentum. Okay, firstly, this is question 4. And then 4.1, you know how I am with definitions. You guys have them in your textbook. I'll just say it in words. So what is the conservation of linear momentum? Well, that is basically saying that the total momentum in a system is conserved. I mean, that is just simply put. Okay, or rather you would say in an isolated system, linear momentum is conserved. Okay, I would stick to that. Or it remains constant. Any of them. Just mention isolated system. Linear momentum is in an isolated system, linear momentum is conserved, right? And then we are good to go. Conserved remains constant. That's pretty much what you could say. Okay, now 4.2. Calculate the magnitude of, okay, firstly 4.2.1, the velocity of trolley Y immediately after the collision. Remember, initially trolley Y has a velocity of 0 because it is at rest, but somewhere, somehow, you're going to have a final velocity. Okay, so we're going to use the principle of conservation of linear momentum in order to calculate the velocity then. And you can see it's 4 marks, so we're going to do quite a bit of work. Okay, so let's do this. We're going to say momentum before. Okay, yeah, let's just say momentum before. My goodness, momentum before is equal to momentum afterwards. Okay, and we're going to look at the momentum of trolley X as well as Y. So the sum of the momentum before and after, they're equal. So momentum is simply mass times velocity. So mass of trolley X and the velocity of trolley X initially plus mass and velocity of trolley Y all initially is equal to the mass and velocity of trolley X finally plus the mass and velocity of trolley Y finally. Okay, you can write it much better than me. So we know the mass of X is 1,2 and the mass of Y is 0,5. So 1,2 and the velocity initially was 8. Here we know that this term is 0 because the velocity was 0 initially. Now at the end, we still have the mass of 1,2. The velocity there was 4, so it was halved, okay? And then we are looking for the final velocity of trolley Y. So we have 0,5 and final velocity. So if we're going to put final velocity as the subject of the formula, we're going to get 1,2 times 8 minus 1,2 times 4, and that will be all divided by 0,5. Okay, I hope I'm not missing anything. And then we can then get the final answer. So let's take out our calculator and simply put the 1,2 times 8 minus 1,2 times 4, and that is equal to 0,5. Sorry, divided by 0,5, and the answer is equal to 9,6. Okay, 9,6 meters per second. Oh my word, so it went from 0 to 9,6. My goodness. Okay, and then 4.2.2. Calculate the magnitude of the average net force trolley X exerts on trolley Y during the collision. So at that portion where you have that gradient going down, that's the portion we're going to actually look at. And in order to do that, I hope you know that the area under the velocity time graph actually will give you the force. Okay, why do I say that? Remember that velocity, I'm going in many directions here. Okay, so net force, you can fast forward if you're not interested in this part, but the net force is equal to mass times acceleration. And then acceleration is equal to the change in velocity over the change in time. And that is what we can see in that triangle over there, y. because we have the change in velocity, we went from 8 all the way to 4, and the time as well, we went 20,1, okay, to 20,2. So if you were to put that in XY coordinate, if I could say. So now when it says the average net force that trolley X exerts on trolley Y during the collision, you can simply take the area under the graph, or you can simply just calculate it yourself, which is pretty much the same thing. So the mass, so average net force, the mass of trolley X is 1,2 kilograms. And the change in velocity, so we went from 8 to 4. So I'm just going to say 8 minus 4, and then 20,1 minus 20,2. Okay, and they want the magnitude. So in this case, the negative value doesn't really matter. They really just want the magnitude. So you have 1,2 multiplied by 4 all over 20,2 minus 20,1 is simply 0,1. So yeah, we get 48 Newton. Okay, and then 4,3, it says, is the collision elastic or inelastic? How do we determine elasticity? Well, we have to look at kinetic friction. What am I saying? Kinetic energy. It's been a long day. Kinetic energy. So we're going to look at the kinetic energy before the collision and the kinetic energy after the collision. If both of them are equal, then yes, we have an elastic collision. But if they're not equal, we do not have an elastic collision. So it's basically inelastic. All right. So we're going to do the sum of kinetic energy, not kinetic friction. Kinetic energy. All right. And we're also going to look at it. Yeah. So kinetic energy. Finally. Okay. So we know initially trolley Y doesn't have any kinetic energy because it's stationary. So we're just going to look at the one for trolley X. Okay. So it's basically half mass times velocity squared. So the mass is 1,2. And I'm just going to put on the side there that kinetic energy is equal to half mass times velocity squared. Okay. So mass and then velocity was 8. So that is squared. And then afterwards we have half, actually, let's not put the equal sign as yet because we don't know if we do have elastic collision. So we have half mass, which is 0,5. And then the velocity afterwards was 4. And then we have half mass, sorry, this is the mass of trolley Y. So this is half mass times velocity squared, and then for trolley Y we have 0,5 as its mass, and its final velocity that we calculated is 9,6. It actually makes sense that it moved that far because the mass is lower. Okay, so yeah, in case you're wondering, why would it have a bigger velocity than trolley X initially? Okay, so yeah, that is that. So let us go and calculate then what are we going to get this side and what are we going to get that side. So we have half multiplied by 1,2 multiplied by 8 squared. I mean, we can already see it's inelastic. It's inelastic, guys. We have 38,4 this side, joules. And then we take the very same. Okay, we have 9,6. And then we're going to say plus half times, half times a half times 9,6 squared. I was wrong. These halves make a difference. Yo, I take that back. Hey, I saw the 9,6. I forgot that we have half times a half. But yes, I was right. It's inelastic. They're not the same. I actually thought the final kinetic energy is going to be more than the initial. But they are not the same. That's what I'm trying to get at. We can see that the kinetic energy initially is way higher than the kinetic energy finally. So this is an inelastic collision. All right, and if they ask for a reason for inelasticity or inelastic collision, we just say that it really has to do with the fact that the kinetic energy, or the sum of the kinetic energy before, is not equal to the sum of the kinetic energy afterwards. And that concludes question 4. Thank you for tuning in. See you next time.
Well, welcome to MV Tutors. My name is Fiarahle Manana, and we are still doing the November 2022 Physical Science Paper 1. We are now in question number 5, and let's get right into it. It says, a 12 kg block is initially at rest at point A at the bottom of a rough inclined plane. Okay, so it starts at A. The block is pulled up the incline by a constant force F acting parallel to the incline. The block reaches point B, there it is over there, which is at a vertical height of 4.5 above the horizontal, with a speed of 2.25 meters per second. See the diagram below, right over there. Oh, by the way, please like and subscribe to our channel. We really appreciate it. Okay, getting back to the questions. The first one says, define the term non-conservative force. Well, a force is really non-conservative if it's pushing something. If let me just write it. If it's pushing something and it's non-zero, basically. Let me just write that down for you. 5.1. Well, a force is non-conservative if, okay, I wrote it down here, the work it does, if the work it does in moving an object in a closed system, is non-zero, which means it's actually work. It's actually non-zero instead of it's a value. Okay, let's look at question 4.2 now. It says, draw a labeled free body diagram for the block when it is pulled up the inclined plane. Okay, let's do that real quick. This is now 5.2. So in drawing this, you can see that the force is basically on an incline. So we're gonna draw, let's start with the force because that's what we've been given. Okay, that's F, and we know that weight, which has a force of gravity, is always moving down. We'll call it weight. Okay, furthermore, this has a normal, and the normal is always perpendicular to the plane, and the plane is going that way, so it's perpendicular right here. Okay, and then furthermore, the last thing that we have is a force of friction, which is always moving opposite the direction of movement. Okay, the force. So I'll just call it FF. Okay, friction force. That's it. Okay, so it says calculate the work done on the block by the non-conservative forces when the block moved from point A to point B. Okay, so what we're going to do at this point is just scroll down to the formulas. Let's look for the work formulas. Where are they? There we go. There we go. There we go. That's what we're looking for. Okay, so the work one that we're going to take, we're going to use is work is equals to change in kinetic energy plus the change in potential energy. Yeah, right here. And then furthermore, we know that kinetic energy formula that we are given there is given by half mv squared plus potential energy is given over there. It's just simply mgh. Okay, so those are the formulas that we need. Let's go back now to the question. Now, when it comes to the expanded formula, because we're using an expanded formula here, I'm just going to rewrite it here. It's going to be a half, and then m doesn't change, but the velocities change. We will have a final velocity at b, okay, minus the initial velocity at a. Okay, that's going to be squared. Mass doesn't change, gravity doesn't change, but the h changes the height. So we once again, it's a final height minus the initial height at a. Okay, let's go in now and put in the numbers. So a half stays a half. The mass, are we given the mass? We're told it's 12 kg, so there we go. Final velocity, we're given that the speed, here it is at b is 2.25. 2.25 minus, initially we told that the block is at rest, so that's a 0 velocity, plus the mass is still 12 kg. Gravity is just 9.8, it doesn't change. And then the height, the final height, we're given 4.5 over there. 4.5 meters minus the initial height is 0. Okay, so now we just gotta put this in a calculator. Let's go for it. So basically we have a half, so I'm just gonna put 0.5 times 12 times 2.25 plus 12 times 9.8 times 4.5. There we go. Let's change it to a decimal, and our final answer is 542.7. And our work done. Made a fundamental mistake here. I forgot to square this. This should be squared. Okay, so now we need to go back on our calculator. That 2.25, it needs to be squared. That's a common mistake that everybody knows, so I'm not gonna re-record this. Simply just gonna realize my mistake and correct my mistake. This is something that you should learn as well, to correct your mistakes. Okay, because in life mistakes happen. Not everything is gonna be perfect. I'm just gonna write it in 2 decimals, so I'm gonna put 5.8. There we go. Okay, now we can conclude. The work is 559.58 joules. Let's look at 5.4 now. It says the same constant force F now moves the block at constant velocity, which means acceleration is 0, across a rough horizontal surface from point B to C as shown below. Force F acts parallel to the horizontal surface. There we go. The magnitude of the constant friction force acting on the block while moving from point B to C is 42 newtons larger than the magnitude of the constant friction force acting on the block when it moves from point A to B. Okay, let's put that into perspective, okay, so that it's clear what we are doing. So you've got this horizontal. We've got point A to B and then to C. So what they are saying is that, okay, let's start here. Let's start here with the horizontal. Okay. Horizontal has, first of all, they tell us that this force is constant. It's the same force on AB and on BC. Same force. The difference is with the frictions. The friction here, which I called FF, friction force, they are saying that the horizontal friction force is actually 42 newtons larger. So it's like it's the same friction force, but here on the horizontal there's an added 42. Okay. All right. So that's what they're saying in this diagram. Now that we have our clues, let's go read the question. Calculate the distance from point A to B. So they want the distance from A to B. We need a formula that has distance and work. Okay, because we just solved work. Sometimes these questions are cumulative like that, where you have to use previous information to kind of solve the next question. Okay, cos theta. So we're gonna, that's the work. This is a formula. It has distance and work. Now that we've got the right formula, let's go back to the question so that we could start using this formula in the question. Okay, so right, we have work done. We just solved it above. We don't have F. Let's solve for F. Okay, so let's look at it from B to C. We can see there clearly that they are opposing each other. So F is equals to the friction force plus 42. Okay, and then we're gonna take that F, we'll take it to point A to B. We're looking at A to B now, and we have there that we have F is also opposing the friction force. Okay, but we can write this F in terms of the friction force since it's the same force. So instead of F, we'll put the friction force plus 42 minus the friction force again. Okay, so that's from point A to B in terms of forces. You can clearly see that they are opposing each other. Okay, so we're using this formula. Okay, let's just write it again so that things flow really well. Okay, change in distance and then cos theta. So the work done, we solved it to be 559.58. Okay, this force is the entire force that is acting on A to B, and it's given by FF plus 42 minus FF. Okay, it's this one that we just solved over there. And then we have the change in distance, and then we have the cos theta. Let's just do the mathematical gymnastics now. So the 559.58 stays as it is. This side, these are like terms, the frictional forces, they subtract each other. So I'm left with 42, and then change in distance, and then cos. Now my theta is going to be 0 because these forces are in the same direction as what? The plane. Okay, So now what I'm gonna do is just make change in direction, the subject of the formula. So 559.58 divided by 42 and cos 0. Well, we know that cos 0 is 1 basically, but anyway, for the purposes of this calculation, we'll just put it there. Okay, so we have 559.58. That's gonna be divided by 42 is cos of 0, close the bracket, and I want it in decimal. It's 13.32. Okay, so that's our final answer, but just to put it in standard form, I'm just gonna say therefore the change in distance is equals to 13.32 meters. That's it. That's our final answer right there. Well, thank you so much. This is the last question. I hope yes, it is. Wow, that's it from me. Please remember to like and subscribe to our channel if you learned something today.
Hello everyone and welcome to MV Tutors. I'm Solo and I'll be looking at question 6 with you guys from the physics paper. Please don't forget to like our videos and subscribe to our channel, and let's get right on with it. So, a learner investigates the relationship between the observed frequency and the frequency of sound waves emitted by a stationary source. Alright, so the source is stationary, you know the velocity is 0. Now the learner moves towards the source at a constant velocity and records the observed frequency for a given source frequency. This process is repeated for different frequencies of the source, with the learner moving at the same constant velocity each time. The graph below shows how the observed frequency changes as the frequency of sound waves emitted by the source changes. Alright, so we can see that the relationship is quite linear. As the frequency of the source increases, so does the frequency of the listener. So let's see and let us answer questions that follow. Alright, so we need to, for 6.1, just right there, question 6. Okay, 6.1, name the phenomenon illustrated by the graph. Alright, so as soon as we talk about the frequency of the source and the frequency of the listener, we know that we are dealing with the Doppler effect. Okay, I hope that you see that and know that. And if you didn't, well, in most cases, question 6 deals with the Doppler effect. Alright, and then 6.2, it says name one application in the medical field of the phenomenon in question 6.1. So for those who have or who are pregnant and you go for your sonar, the scan, so the Doppler effect can be used to determine the heartbeat of a fetus. All right, so that's one of the applications. Another is to determine the blood flow. Okay, so yeah, I'm just gonna go with the first option there, heartbeat of fetus. So determining the heartbeat of a fetus. All right, and there are many more. Okay, so 6.3, write down the type of proportionality that exists between the frequency of the listener and the frequency of the source as illustrated by the graph. So we can see here that the frequency, like we said, what we observed, the frequency of the listener is directly proportional to the frequency of the source. Okay, so this question is going quite fast. 6.4. The gradient of the graph obtained is found to be 1,06. Remember gradient, let's do this. So gradient m is equal to delta y over delta x. And in this case, our delta y would actually be delta frequency of the listener over delta frequency of the source. And they tell us that that is actually 1,06. Okay, it was almost a one-to-one relationship. All right, and then now they say if the speed of sound in A is 340 meters per second, calculate the magnitude of the velocity at which the learner approaches the source. All right, so we know that the speed of the source is 0 because it's stationary, and we're looking for the speed of the listener. We know speed of air is 340 meters per second. Okay, and if you are like me and you have forgotten the Doppler effect equation, not really forgotten it, but yeah, you just need a refresher and just need to be sure, you're going to go over to the formula sheet and have a look at the equation given. So we see that the frequency of the listener is equal to the velocity. Okay, so we are going to talk about whether we have a plus or a minus there. Okay, frequency of volume of, did I just say volume? Velocity of listener. Then we have speed of sound and speed of the source. Okay, and all of that is multiplied by the frequency of the source. And so the question is, if you have a stationary source, it doesn't really matter whether it's plus or minus because you're just adding or subtracting 0. Okay, it's stationary. But in the case where you have the listener going closer or headed towards the source, what do you use? Is it a plus or is it a minus? Okay, so in this case then we're going to have a plus, and these are just one of the conditions that you need to know. Whether the source is moving towards the listener or the listener towards the source, that's you'll know whether you're going to put a positive or a negative. And if you forgot, please do head over to our playlist for the physics lessons where I do address this in the Doppler effect topic. Okay, so we've got you, sorted you out. All right, now let's go back and see what we have. Okay, question 6, there we are. We are looking for the magnitude of the velocity at which the learner approaches the source. Please be reminded that they gave us the gradient of the graph, all right? So frequency of listener over frequency of source is equal to 1,06. So what we can do, we can divide by the frequency of the source on both sides. Okay, there we have frequency of listener and we have frequency of source. We have the speed of sound and then the speed of the listener, and then we just have 340 because the source is stationary. All right, so we know this is 1,06, right? And then we can actually just multiply it by 340 while we're at it. Okay, and then subtract 340, and then we're left with the speed of the listener, or the velocity, and we're going to calculate the magnitude. So we're just going to head over to the calculator over there, and it's going to be 1,06 multiplied by 340 minus 340. Wow. No, 340, I'm thinking this is a very big answer, my goodness. How fast was this person walking? They were not walking, they were actually sprinting. Yeah, it's still quite big. Okay, so the velocity of the listener, my goodness, 20,4 meters per second. Were they walking? This is a lot. This is a lot. But yeah, so that is what, 5 marks. Okay, and yeah, let's head over to the next question. I guess it is what it is. Wait, what is this learner doing? Okay, the learner moves. We don't know how they're moving. They could be in a car. They could be on roller skates or on a skateboard. But 20,4 meters per second is quite high. All right, so anyway, moving on. So it says the investigation is now repeated with the learner moving at a higher constant velocity towards a sound source. Okay, so now they're saying the velocity increases now. Okay. So 6,5 the velocity has increased compared to the first scenario. Now it says copy the graph above in your answer book and label it as A. Okay, on the same set of axes, sketch the graph that will be obtained when the learner is moving at the higher velocity. Alrighty, so let's just copy the graph over. In your case, you would have had the graph in your answer sheet. So yeah, so oof, my goodness. Alright, let's try that again. Okay, it doesn't matter how it comes out, let's just do it. Alright, and then we had A looking something like this. Okay, so yeah. And that is A. Ne? And now, if the speed has increased, what will happen? Will the graph become flatter or will it become steeper? Okay, and yeah, so let's have a look actually. I forgot to label the graph. So this is frequency of learner, and that is frequency of frequency of the listener, and this is the frequency of the source. Okay, so if we look at our equation over here, what would happen if you increased the velocity of the listener? Okay, if you increase the velocity of the listener, let's look at this equation here. If you increase the velocity of the listener, this entire sum would increase. Okay, yeah, so okay, let's just go to this equation. If you increase the velocity of the listener, in this case, then the frequency of the listener would also increase. All right, and you'd probably get a steeper gradient. Okay, because your ratio or your gradient, frequency of listener divided by frequency of source, will increase as well. Okay, I hope that you are seeing this. So if we were to then sketch the graph of B in this case, we would get it to look something like this. I mean, they don't need values, you just need to show that it is steeper. Okay, and there you go, that's where you would have B. All right, and this is question 6, just 10 marks. Yeah, that's it.
Well, welcome to MV Tutors. My name is Fiaga Semanana, and we're still doing the November 22 Physical Science Paper 1. Okay, now let's get right into it. We are now in question number 7. It says a charged sphere M is suspended from a ceiling by a light, inextensible, insulated string. Okay, there we go. We can see it. It says another charged sphere N of mass that and carrying a charge of that hangs stationary vertically below sphere M. The centers of the spheres are 0.3 meters apart, as shown in the diagram below. Okay, we can see it. State Coulomb's law. Now, when it comes to Coulomb's law, you really just want to check out the formula that you have been actually given in your formula sheet. There it is. Where it is? Where is it? There it is over there. You're just basically putting this in words. Now, I didn't want to waste much time, so I wrote it right here. But let's go right through it. It says the magnitude of the electrostatic force. So that's that force they're talking about there, exerted by one point charge on another. So the point charges they're talking about is Q1 and Q2. Okay, is directly proportional to the product of the charges, meaning you're multiplying the charges. That's what they mean by product. And inversely proportional to the square of the distance between them. So that r squared there, that's the distance between the point charges. So you basically just describing the formula as it stands. Okay, so that's with that one. It's purely just theoretical work at this point. So I would like to move into the next question. Okay, so it says state. Now this is not, we're now looking at question 7.2. It says state whether the charge on sphere M is positive or negative. Now, given that sphere N is positive, for these points to attract each other, it means M must be the opposite of positive, which is, if you said negative, then you are correct. It should be negative, just like that. Okay, now let's go to the next question, which is 7.3. It says, draw a label free body diagram for sphere N. So we got sphere N right there. Now, there's a force between them. Okay, that's Fe. I don't know why I just did it like that. It's weird. It's weird. It really is. So I'm gonna get rid of that and rewrite it. So I'm gonna put an arrow and then I'll put Fe. And opposite that force, we know that sphere N has actually a weight, okay, which is mass times gravity. That's what weight is. Okay, now moving on very swiftly, let's look at question number 7, or rather 7.7 what is it? 7.4. We're on 7.4 now. It says calculate the magnitude of the charge on sphere M. Now let's use the formula that we just came up with, Coulomb's law. It's Q1, Q2. But instead of Q1 and Q2, we're gonna have Qm and Qn. Okay. Now this force, as we can see from the this free body diagram, that it's this force that we're looking at here, and we can see it's opposite the weight, which means we can calculate. Remember, when we calculating weight, we always say it is actually mass times gravity. So what's the mass that we've been given? The mass we've been given here as 2.04 times 10 to the negative 3. Okay, and then that's times 9.8. Okay, so we just did mg. Now that's going to be equals to k. K is a constant, which is always 9 times 10 to the power 9 times, for q1 we're going to make it qm, or let me make it qn, which is what we've been given as 8.6 times 10 to the power minus, now I can't tell, is that an 8 or a 9? It looks like an 8, so I'll put an 8 times now the qm. Okay, so that's represented by q2. Now all of this is divided by the distance between them, which is 0.3, and it must be squared. From now, all I need to do is mathematical gymnastics. I will do them for you because I know that some of you really struggle with these mathematical gymnastics. So I just rewrote this. Okay, but what I'm going to do is get rid of this fraction by cross multiplying. So on top here comes 0.3 squared, right? And then at the bottom, if I cross multiply, you get that whole thing of 9 times 10 to the power 9 times 8.6 times 10 to the power minus 8. Okay, so all of this will give me qm, which is what we are looking for, the magnitude of the charge of sphere M. From here, I need to put this in a calculator. I put my fraction 2.04 times 10 to the power negative 3, and then I come downstairs, times 9.8 times 0.3, all of this is squared, come downstairs, it's 9 times 10 to the power 9, down, times 8.6 times 10 to the power, I really hope that's a minus 8, hey? I really do. Okay, so we get that qm then, therefore that charge of m is 2.32 times 10 to the power minus 6. Now what are the SI units? Coulombs. Okay, all right, now moving right on along. 7.5 are we? Okay, how does the electrostatic force that sphere M exerts on sphere N compare to that exerted by sphere N on sphere M with respect to that? Okay, let's do those questions. Now let's go purple this time, and it's 7.5.1. Well, when it comes to magnitude, it's the same magnitude. They're sharing it. The magnitude is literally the same. Okay. But when it comes to direction, they are opposite each other, because remember, they're attracting each other. So if the other one is going south, the other one is going north, so that they meet. So it's an opposing effect. They're opposites each other. That's the direction. Okay, let's look at this last calculation. It says point X is 0.1 meters vertically below the center of sphere N, as shown below. M and N. Okay, we see that. Calculate the net electric field at point X. Now, before we do that, okay, there's something that I'd like to do. Okay, I'd like to start with naming a direction. Let's choose a direction up as positive. Okay, upwards is positive. Now that we've done that, we know that the sphere M is actually negative. Okay, and we know sphere N is positive, okay, as given in this question. So we to get the net electric field, we need the net one. Okay, we're gonna take the electric field of N because it's positive, and then we're gonna subtract that one of M because it's negative. Okay, so while N is moving upwards, M is moving downwards in a negative direction. That's how we're gonna get that. But before that, let's go fetch our formula for that. There it is. It's equals, so E, that's the electric field, is just K, 1Q, and then the distance squared. Okay, now we're in a position to go back to our question and start answering it. Okay, remember we said we'll start with En, so let's start with En. K is just 9 times 10 to the power 9, it's a constant. The charge of N, we were given, N was given as 8.6 times 10 to the power, what's that, minus 8. Okay, that's cool. Divided by the distance. Okay, the distance of N from X is 0.1, so it's just going to be 0.1 squared. So we're going to subtract EM. Okay, M is going down, so it's negative, so we're just going to go 9 times 10 to the power 9 times, we calculated that charge, 2.32 times 10 to the power negative 6. So 2.32 times 10 to the power negative 6. It's all divided by, now the distance between this is 0.1 plus 0.3, which is 0.4. 0.4, okay, meters away from XM. Okay, so we're ready to put this in a calculator. There we go. And then we go 9 times 10 to the power 9. We go down times 8.6 times 10 to the power -8. Okay, that's all. And then we go down, it's 0.1 squared. Go sideways and we go minus. We put another fraction. Sorry about that. That was thunder. Okay, so we've got 9 times 10 to the power 9. We go to the side times 2 point, was it 32 or 23? I can't remember now. 32. It's fine. 32 times 10 to the power -6. Then we go downstairs. That's a 0.4 distance and it must be squared. It's our final answer. You know what we did wrong? This charge here is a negative charge. Remember we said M is negative. Okay, so a negative and a negative makes a positive. So this answer here should actually be positive. 53,100. And remember what we said with our direction. We said positive is up. So this is upwards because it's positive. But when it comes to units, units are always going to be newtons per coulomb. It's not per, it's just coulomb, because if you look at this, we've got newtons and coulombs. Well, I hope that's all that I really have for you. There's really nothing much else. It's just confirming it's newtons per coulomb. That's the final answer, and we'll stop right there. Okay, now see you on question number 8. Otherwise, please like and subscribe to our channel at this point. We'll appreciate it very much.
Hello and welcome back to MV Tutors. I'm Solo and I'll be looking at question 8 with you guys. Please don't mind me and my scarf. I'm a bit under the weather as we are transitioning from summer to autumn. Yeah, some of us have flu. So yeah guys, let's read what it says. So we have a circuit diagram below that shows 4 resistors connected to a battery of EMF E and internal resistance R. The resistances of the ammeter and the connecting wires are negligible, while the voltmeters have very high resistances. Okay, so we see we have a very interesting circuit diagram over there. And we're going to start first with Ohm's law. And before we do, please don't forget to like our videos and subscribe to our channel. Yeah, we really appreciate for those who are already subscribed and those who like our videos. Thank you very much. So yeah, let's state Ohm's law in words. I'm not going to write it down fully. And please feel free to add more definitions to the comment section. Okay, so basically Ohm's law says that the potential difference across a conductor, okay, is directly proportional to the current in the conductor. Okay, I'm just going to say I. All right, at a constant temperature. So this is only applicable if you have constant temperature. Very important. Okay, and now they tell us that switch S is closed and the reading on the ammeter is 3.5 amperes. Remember, when the switch is opened, you don't really get a reading on there's no current. Okay, well actually it does flow through if we're looking from the positive side. On the E side, I can't really sketch, but we have the positive. So you have current coming through, but as soon as it reaches the open circuit, it just freezes. Okay, Anyway, that's not what we're looking at right now. Let's get back to the question. So 8.2.1, it says, calculate the total external resistance of the circuit. Okay, yeah, we have an interesting circuit over there because you have the 4 ohm resistor and you have the 1 ohm resistor, right, and other things. Then you have the 2 as well as the 3. So I think let's first deal with the 2 and the 3 ohm resistor, which gives us 5. Ne? 2 plus 3, because you can just add those. So now you have 5 ohm and you have 1 ohm as well as 4 ohm. So let's deal with the resistors that are in parallel. So 1 over resistors in parallel, we have 1 over 5 plus 1 over 1. I think let me just make it 5 over 5 so that we have the same denominator. Alright, so then we have 6 over 5, and if we want to get our resistor in parallel, we're just going to swap around the 5 and the 6. Let me just fix the screen. It's misbehaving. Okay, so then our resistor in parallel will be 5 over 6. And what is 5 over 6? Where is my calculator? Okay, it's nowhere to be seen. I'll deal with that later. So that is the resistor in parallel. Okay. We have now made it in series. So now we have 5 over 6 over here. Okay, and now to get the total, so our total, it will simply be 5 over 6 plus the 4. Let me just make everything all over 6. So if I have this, 6 times 4 is 24. So now we have 29 over 6. Okay, now I really need the calculator. Let me get it quickly and then we'll finish off this. Okay, so now we have the calculator and we can say 29 divided by 6 and we get 4,83. Alright, so that is the total resistor in the circuit, 4,83 ohm. Okay, that's a nice 4 marks. Now 8.2.2. Calculate the reading on voltmeter V1. Okay, so that is the voltmeter across the EMF, okay? And the internal resistor. So here, using Ohm's law, we are going to use the full current, which is 3,5 amperes, and the total resistance. Okay, so we're going to say this times 3,5. Okay, so it's going to be 16,92. 16,92. Let's see, is it 92 or 91? Yeah, 16,92 volts. Okay, and then 8.2.3. How does the reading on voltmeter V2 compare to the reading on voltmeter V1? Okay, so in this case, voltmeter V1 is 16,92. If you wanted to get voltmeter V2, you would have taken it would be, if you had resolved the two resistors, it would have been 5 ohm, right? So basically the reading across the 5 ohm resistor. And remember, when the current flows, because the circuit is closed, you were going to have 3,5 amperes here. Then some of it would have gone this side, and then not all of it, just a portion of it goes to the 5 ohm resistor. So a very small amount, than 3.5 multiplied by 5, maybe let's say 2 multiplied by 5, that's like 10. So the reading on voltmeter V2 is definitely going to be smaller than. Okay, I hope you see that and agree. So it is smaller than. Alrighty, and it's just 1 mark. Let's go to 8.3. Okay, so a learner concludes that the EMF of the battery is equal to voltmeter V1. Is that true or what? Well, it depends. And I see that 8.3.2 does ask if we agree or not. So we'll get there. Let's not jump things. But let's go to 8.3.1. So it says define the term EMF. Again, I'm not really going to write that down. I'm just going to say it, and I'm sure you guys also know it as well. So the EMF is basically the maximum work done by the battery per unit charge. Okay, so we'll say maximum work done by a battery per unit charge. Okay, it's gonna say unit charge, unit Q, unit charge. Okay, yeah, you understand. You'll write it properly in words. All right, so that's 8.3.1 and 8.3.2. Is the learner's conclusion correct? Yes or no? Well, it depends. It depends. The voltmeter would be the same as the EMF, provided there's no internal resistance. So in this case, I would say no. Okay? Because of the internal resistance, no. If there wasn't any internal resistance, then yeah, it would be. Okay, so give a reason for your answer. It's also like 1 mark. So we'd say that the battery has internal resistance. Okay, that's because of the internal resistance. Okay, and we are done with that. Oh, there's now another circuit. Okay, no, same one. Yes, same one. Okay. All right, so now switch S is removed and replaced by voltmeter V2 as shown in the circuit diagram below. All right, and now we're gonna just talk about what's gonna happen when the following changes. So 8.4.1, how will each of the following change? So we need to choose from increase, decrease, or remain the same. All right, so 8.4.1 says the power dissipated by the 4 ohm resistor. Okay, so what is power? Can you go and look at the formula sheet, but I think it's V times I, but let's just make sure. Let's be sure. Let's not guess. Okay. Yes, so yes, power is VI, and we can then from that VI get other things, or we could say it is I squared times R, or we could say is V squared over R. Okay, let's go back to the question and see. So how will each of the following change? The power dissipated by the 4 ohm resistor, you can see where the 4 ohm resistor is. All right, if we have voltmeter V2 over there. So will it increase, will it decrease, or will it remain the same? In this case, it would. Okay, so they didn't ask us why the power would decrease, but I would say that because now we have V2 that is introduced, voltage in series, because it would be in series with the potential difference at resistor 4. It actually divides, so your voltage before would be much higher than the voltage after V2 is added, all right? And so your power would then decrease because your voltage decreased. So that's 8.4.1, and then 8.4.2, the reading on voltmeter 1, well, that will increase, okay? And I'm reserving my reasons for 8.5, which says, explain the answer to question 8.4.2. Okay, so I'm going to try to explain. I don't think I will write it down. But basically, if we add the voltage, they did tell us that the voltages or the voltmeters actually have very high resistance. So by adding voltmeter 2 with a high resistance, you won't get much of the current passing through the 1 ohm resistor. Okay, much of the current will go to the resistors in parallel. And so the resistors in parallel have an increase in voltage. Okay, and then another thing is the total resistance in the circuit will increase. Like I said, the more voltmeters are added, they have more resistance. So if we have more resistance, V is equal to IR, V will increase. Okay, another thing is the current in the circuit decreases. Okay, yeah, and then lastly, I would say that the internal resistance there by the battery, that will decrease. So your lost volts will decrease, and if your lost volts decrease, your V1 is going to increase. Okay, so the reading on the voltmeter 1 would increase. Okay, let me just write down then what I said. So the current, first of all, what I said, through resistor 1 is quite low, it's negligible. Okay, therefore you have an increased current through the parallel resistors. Okay, therefore the voltage there increases. Okay, and then also what else did I say? I said the internal resistance would decrease. Okay, small r will increase, so your lost volts will decrease, whereas your V1 would increase. And I also said that because you are adding a voltmeter, and voltmeter has a higher resistance, your reading at voltmeter 1 will increase. Okay, and then overall your current in the circuit decreases. And that's it, that's the 4 marks. So we are done with question 8. I managed to survive in the middle of flu, but it is what it is. Thank you for tuning in, and see you guys next time. Hello everyone, and welcome to MV Tutors. I'm Tulu, and I'll be looking at question 9 with you. Please don't forget to like our videos as well as subscribe to our channel. Alright, so let us do this. Question 9. Okay, so it says the diagram below shows the initial position of the coil in a simple DC generator. The coil is rotated in an anti-clockwise direction as shown. 9.1.1, name the component in this generator that ensures that the induced current in the external circuit is in one direction only. Alright, I hope you can see it over there, and that is the split ring. Okay, so let's just write it, 9.1.1, that is the split ring. Okay, 9.1.2 is the direction of the induced current from X to Y or from Y to X. Alright, so because we have a generator, we can use the right-hand rule. Okay, Fleming's right-hand rule. Remember, your index finger shows you the direction north to south, alright, and your middle finger will be your current, okay, and your thumb will be the thrust. So left to right, we see that the thrust is downwards and the direction is it's coming in my it's coming to me. All right, so it's from Y to X. I hope you can see. Oh gosh. All right, yeah, but yes, so it's in the direction, so current is in this, coming to me in my direction, so it's from Y to X. Okay, but you could have also said that, I mean, you can't really see that the wires are connected to some source. All right, so you could say there's no current. It's an option. Okay, all right, and then 9.1.3. So before we even get there, it says a maximum voltage of 90 volts is generated when the coil is rotating at a frequency of 20 hertz. Okay, now 9.1.3, write down the time taken for the coil to complete one rotation. So yeah, the equation we're going to use is T period is equal to 1 over frequency. Okay, and what was the frequency? It was 20 hertz. So what is 1 divided by 20? I'm going to use a calculator. I think it's, yeah, 5%. Okay, so we're going to have there 0.05, I almost wrote 5%. 0.05 seconds. Okay, cool. Now 9.1.4. The coil starts rotating from the initial position as shown in the diagram above. Sketch a graph of output voltage versus time for one complete rotation of the coil. Indicate the maximum voltage and the relevant time values on the graph. So we know it takes 0.05 for one full wave, right? And we have a maximum of 90 volts. And also we have a DC generator. It's not alternating current where you have like a sine or cos wave. This is literally like bounces. Okay, so let us attempt to draw this. Okay. All right. My whiteboard has changed a bit and I am not used to this, so I can't even draw a straight line. But let us see. So this is our y-axis and that's our x-axis. Let us just attempt. So if it's a full wave, that's going to be at 0.05 seconds. All right. And halfway through, that'll be 0.025 seconds. And you know that our maximum is 90. Okay. You can either draw it from the positive side or you can have the negative side. But I'm just going to draw it on the positive side of the y-axis, and that is your voltage over there. So yeah, so at this point we're gonna have it looking like this. Okay, not a bad attempt. Right? So yeah, it's not bad. And like I said, I mean, you could have also done it like this, but I'm not really a fan of drawing upside down graphs unless if it's really necessary, but either or works. Okay, and that is 4 marks. Yes, so sketch the graph. We have the maximum voltage, the times are there. I think we're done with this graph. Okay, so 9.1, oh, 9.2. Oh, we're almost done. Quite a short question. So it says wall sockets supply RMS voltage and current. All right, so a 220 volt AC voltage is applied from a wall socket to an electric kettle having a resistance of 32 ohms. Calculate the average energy dissipated by the kettle in 2 minutes. So what information do we have? We have the voltage, all right, which is 220 volts. We have the resistance, which is 32 ohm, and then we have time, which is 2 minutes. We work with seconds, remember? So 2 times 60, that is 120 seconds. And we are looking for the energy dissipated. Remember that power is equal to the work done over a certain time. Okay, so work is measured in joules, that is energy. So now work is equal to power times time. Okay, so now we're gonna look at our formula sheet and see the formulas we have for power. Okay, actually let's go to, yes, this one. And what information do we have exactly? So we have, I almost said velocity, we have voltage, and we also have resistance. So I would go with the equation of power being equal, or the average power being equal to V squared, V RMS squared, over R. I think this is what we can work with. Okay, so V squared, or V RMS squared, okay, RMS squared over R multiplied by time. All right, and our voltage is 220 squared, our resistance is 32, and the time that we have is 120 seconds. So let's see if we plug all of that into the calculator. What do we get? Okay, so 220 squared divided by 32 multiplied by 120, we get 181,500 joules. Okay, so let's just check if that's the last question. So calculate the average energy dissipated by the kettle in 2 minutes. That is 181,500 joules. All right, so that's it. Thank you for tuning in. See you. Question. Welcome back to MV Tutors. I'm Tsolo and we are finishing this paper finally. Please don't forget to like our videos and subscribe to our channel. Do tell your schoolmates about MV Tutors. And yeah, please comment below if you have questions, if you have corrections, suggestions, more ways of solving. That really helps. All right, so let's read the question. Light is incident on the cathode of a photoelectric cell connected to a battery and a sensitive ammeter as shown below. So you can see that. Now 10.1 asks, what conclusive evidence about the nature of light is provided by the photoelectric effect? So what do we know about the light? Well, we know that it has dual properties, right? Firstly, there's the particle nature of light and there's the wave nature of light as well. So let's write that down. Why am I even writing? I should just be saying it and you writing it, ne? So light has a particle nature. Other people would say it is quantized. All right. And yeah, so light has a particle nature and a wave nature. Okay, it comes with the particle portion of it, or the particle nature. It's like it comes in small packets of energy. Yeah, and if you want to know more about it, please do check out our lessons. Go to the playlists and you'll see under physics, the photoelectric effect is covered extensively. All right, now let's move on. Question 10, did I just say question 1? All right, so the cathode has a work function of 3,42 times 10 to the power negative 19 joules. Now it says, define the term work function. So work function is basically the minimum energy that is required to get the electrons excited and up, moving about, okay, so that the electrons can be ejected from the surface. So you need that minimum energy. Without the work function, the electrons are just going to sit there and look at you like, bro, come on, okay? So yeah, work function, let me just write it in a more formal way. Okay, so the work function is basically the minimum energy, okay, required to eject electrons from the metal surface. From a metal surface. Okay. And yeah, that was 2 marks. All right, so they did tell us that the work function, let's just write it for ourselves somewhere on some corner, that the work function is 3,42 times 10 to the power negative 19 joules. Okay. Now 10.3, we said before, it says light of frequency 5,96 times 10 to the power 14 hertz is shone onto the cathode. Calculate the maximum kinetic energy of an electron ejected from the cathode. All right, just be careful with that frequency. They didn't say threshold frequency, they just said frequency. Okay, so if you want to calculate the maximum kinetic energy, for those who have forgotten what the equation looks like, please consult the formula sheet. Don't get things wrong unnecessarily. All right, so we can see that the equation that has maximum kinetic energy, especially with information that we know, is this one. So the energy is equal to the work function plus the kinetic, or the maximum kinetic energy. And if I write everything in terms of maximum kinetic energy, I get that we have energy minus the work function. Now we already have the work function. It was given to us in the previous question. So we need to calculate the energy. And we know that energy is equal to Planck's constant times frequency, which we have. All right. So if you don't know where to get Planck's constant, these are the physical constants table. So Planck's constant is 6,63 times 10 to the power negative 34. And the frequency was also given to us as 5,96 times 10 to the power 14. And the work function was also given to us. We wrote it down actually. 3,42, okay, times 10 to the power negative 19. So we're going to put all these values into the calculator and calculate away. So we have 6,63 times 10 to the power negative 34, right? Why did I write 3? Yes. Okay, times 10 to the power negative 34 multiplied by 5,96 times 10 to the power 14. All right, and then we subtract 3,42 times 10 to the power negative 19, and we get 5,31 times 10 to the power negative 20, and the answer will be in joules. 5,31 rounded off to 2 decimal places times 10 to the power negative 20. This is energy, so it's going to be joules. Okay, cool. That was a nice 4 marks. And then now 10.4. The ammeter registers a constant current of 0,012 amps. Calculate the number or the minimum number of photons of light that strike the cathode in a 10-second period. Okay, so let's just write down what we know. There's time there, which is 10 seconds. And there's the current I, which is equal to 0,012 amperes. We know because in order to get the number of photons, which is actually the number of electrons, we're going to use the equation. Number of electrons is equal to the charge all over the charge of an electron, and the charge of an electron is negative 1,6 times 10 to the power negative 19. All right, so we need to get this charge. Okay, my voice is going. And so let's have a look again at the formula sheet. Do we have an equation where we can calculate charge? Alrighty. I guess it's one of those where you need to know your formulas. Not really, not even. Okay, so we know that charge, here they use a small q, but we can use a big Q, is equal to the current times the change in time. And we have all of that. So we have 0,012 multiplied by the 10 seconds. All right. So then our charge is equal to 0,12. Okay, remember the unit for charge? Coulomb. Okay, now we can then go to this formula. So number of electrons is the charge that we just calculated, 0,12 divided by the charge of an electron, 1,6 times 10 to the negative 19. Here, we're pretty much going to take the magnitude, okay? So you don't have to focus so much on the negative because you can't get negative electrons. You get a magnitude of something. All right, so now let's go back to the calculator, and we have 0,12 divided by 1,6 times 10 to the power negative 19. And woo, I hate it when it does this. I need to set it up so that it gives me the answer in scientific notation. Okay guys, I'm gonna sort it out much later, but it's actually 7,5 times 10 to the power 17 electrons. Okay, so I managed to get it to scientific notation, and we can see it's 7,5 times 10 to the power 17. All right, and these are the number of photons actually, which is what they asked. So yeah, electrons in brackets is actually photons. Alrighty, now let us get to the last question. Okay, 10.5. So now it says the intensity of the incident light is now increased. Okay, guys, please go check out the video where we do, like I said, we get into depth with regard to photoelectric effect. And as such, you'll understand what happens if you increase the intensity, if you just keep changing certain variables, what answer are you expecting? So check that out. All right, so now the intensity of the incident light is now increased. How will this change affect the reading on the ammeter? All right, you are increasing the incident light. What will happen to the ammeter? Okay, the ammeter reading will actually increase. And why is that? So as you increase the intensity of the light, the ammeter reading will also increase. And why is that? That is because with an increase in intensity, you have more photons that strike the surface. Okay, and if more photons strike the surface per unit time, the surface of the metal, that is, per unit time, at a higher rate, more electrons become ejected. Sorry, more photoelectrons will then be ejected per unit time, and that would result in an increased current. So let's just recap again. Increasing the intensity of light, you have more photons that are strike the surface of the metal, and with more photons striking the surface of the metal per unit time, especially at a higher rate, more electrons become ejected. Okay, and that results in a higher or increased. I'm not going to write down the answer in words. I think I spoke a little bit too much, but you understood. And that's it. We are done with this question paper. Thanks for tuning in, and we'll see each other next time.